So we will talk about control today. We have a few topics. We will start very basically with control. Then we will have the boat characteristic, which we will measure to gain some insights. And based on that boat characteristic, we will be able to set up our controller quite accurately and quite thought through. Finally, we will also focus on load varying cases. Depending on the time left, that topic can be moved to a later meeting if time does not permit us. So the basics of control engineering, let's be clear, today I will show you techniques to design a controller, but these techniques can be applied on very diverse fields. You can also apply the techniques we will see today on a flow controller or a temperature controller, on a pressure controller. Doesn't matter, these techniques are generally and broadly valid. But as an example case, we will focus on positioning applications, on motion profile positioning applications, and we will also see some things that are specific for that kind of applications. But then I will indicate, in most cases, everything I tell you is generally applicable, and that's also the purpose of this workshop. If you have to design a controller, you should be able to use everything I said in this workshop as practical tips and tricks, do's and don'ts for designing an actual controller. However, if you have a positioning controller, you will have, in most cases, this setup. There is a desired position you want to obtain, and from that, the actual position is subtracted. And that's the basic principle in every control loop, is that you have a desired value and you subtract the feedback value from that. And then you get an error signal. That's the deviation between the desired position and the actual position. You see that's an error in radians, but you use a PI controller to translate that error in radians to a value in rotations per minute, so into a desired speed. And it's quite logical if you think about it. You have a positioning error, you have a deviation in your position. The larger that deviation is, the larger the speed needs to be to obtain the desired position. So therefore, it's quite logical that here this is a connection. A larger error means a larger required speed. Then you have the speed. You can also measure the speed. You have the error signal on the speed, and then you can use a PI controller to dictate the desired current or the desired torque in the motor, because the larger the deviation is between the required speed and the actual speed, the more force and the more energy, the more torque you will need to put in the motor to accelerate to obtain that position. There again, a drive will not apply a certain current or apply a certain torque. A drive can only apply a certain voltage. And therefore, again, you have another cascaded control loop, a current control loop, in which the error in the torque is translated into a desired voltage in volts. That is the setup of a cascaded control loop. 3 cascaded loops here, all to control this positioning application. This is quite typical in positioning applications. However, first of all, if you commission your drive, you will give some data about the motor. And by giving some data about the motor, the drive manufacturer, the drive software, knows the ideal settings of the current control loop, because the current control loop settings only depend on the coils of your motor. You do not need to know anything about your application to have an optimal setting of the PI controller for your current controller. So in most cases, we will only have to design the speed controller and the position controller. Still, there are two control loops, and of course, today we want to tell you how to do that, how to design those control loops. Okay, first of all, I will give the word to my colleague Santiago, because you will immediately test something on the test setup. You will test the response on desired speed. By doing so, we already have some insights and you have already done something hands-on. So now I will give the word to my colleague Santiago, who will guide you through this first demonstration and the first hands-on session.
Hello? You can hear me now? Okay, good afternoon. Mm, so the first demo we will start with is to get familiar with the starter interface. So the idea is to first move the motor and then to produce a step response. So for that we will first focus our attention on the tree project here to the left. So here it's important that we are displaying the servo PMSM, that is the servo motor that we will control. And we also will need to display the open loop, closed loop control and the commissioning. For moving the motor, we will start going to the commissioning. Then we display that. We select or double click in control panel, and this interface will be open. So here we can take control over the motor. So the first we will do is assume control priority. And here is important that always that you get this window, this warning window, you untick this box to avoid to get disconnected from the motor. So you click in accept, and then we will see that this turn yellow. We will tick on enable, and we can see that we have a green button and a red one. So the green one is to turn on the drive, and the red one is to turn off the drive. Here we have also a box to type the desired velocity or the velocity that we want to achieve. So we will first turn on the drive, and then we will give a desired velocity, in this case 500 RPM. Make sure that you don't exceed a limit of 2000. Then you push enter, and then the motor will start to move. It's important to scroll down to see some parameters that you can read in real time. That, for example, the torque and the speed. So the specified torque and the actual specified speed and the actual speed, and the same for the torque. And here you can also see the current of the motor. For me, it's interesting to take into account those two values, especially the torque and the motor current, for further use. So I will keep this value in mind, the torque, 0.34 Newton meters. And now we can just come back to 0 RPM. The motor will stop, but it's always important to click drive off. And also give up the control priority, so we can use the other interface to the one that will help us to produce the step response. If we don't give up the control priority, we won't be able to produce the step response. So I click on yes. And now to produce a step response, we will go on the top view of the starter. We click in device trace. So this interface will be open. Make sure that you are in trace, on the trace tab, and that you tick the right signals. So in this case, we will use the output, which is the actual speed of the PMSM, and the input will be the set point before the set point filter. So this is the speed set point. So both signals should be ticked, and make sure also that these two signals, 9 and number 10, are unticked. This is important to avoid errors. Now here is asynchronous recording should be selected. The factor is 1 for this case, but this factor can change. And always that you change the factor, remember to update here, clicking on this arrow. In this case, we will use 1. So we will record for almost 1 second, or 1023 milliseconds. Here in the trigger, we will use a positive edge. This is actually the signal that we will use for the trigger will be the set point. And we will use a threshold of 10 RPM. So when we pass the threshold of the 10 RPMs, the system will start recording. The idea is also to record it before in advance, so we will use a pre-trigger of 50 milliseconds. Now we can move to the next tab, which is the function generator. Here we will produce our step. So the idea is to choose step speed set point before filter. Make sure that you are selecting the right drive. In this case, we will move the servo motor. So make sure that PMSM is selected. Here we have the signal type. We will use a rectangular signal to produce the step. The three boxes here are the desired velocity or the velocity we will achieve. So here we will move the motor, produce a step of 500 RPM. That's why in the three boxes we have 500 RPM. Make sure wrap up time is 0. The period of the signal will be 1000 milliseconds or 1 second. And the lower limit will be 0 because we want to move from 500 RPM and come back to 0. The pulse width is the time that we want the step or the step time. In this case, we will choose 500 milliseconds or half second. Now we can move the motor or produce the step. For that, we will assume control priority and always remember to tick this box. We will accept. Then we click on the drive on and we will start the trace. So here we can see that the trace is waiting for the trigger. So because the motor doesn't move until now, once it starts to move and pass the 10 RPM, the trigger will be on. Here we start function generator. Then we get a warning message that the motor will move. We click on yes, and the motor will start moving. Then the system itself will send you to the time diagram tab. We stop the drive. Then we right click on the figure and we go to scaling. We click in scaling. We go for the first signal to as curve tab and we select the higher value. In this case, there is just one value, but when you have multiple signals, you will have multiple values and always choose the highest. Then we click OK, just for all the signals, but the last one. Then click on OK, and you can see that the signal is both signals are scaled. So you go here on the right, and you can move your cursor to see the whole response. And here we can see the complete response. Important also, right click also and choose measuring cursor, T measuring cursor, that is on, so you can here read the values for the step response. For example, here, when a cursor is active, you see it with the same color as the curve. And here you see the values for time. In this case, in the point that I am is 24 milliseconds. And the Y value that is 637 RPMs. This is all from the first demo. Now the idea is that you go to the first hands-on. So you do this exercise by yourself. So first locate your number here in the your name here on this slide, and the laptop associated to your name. You will need to go to, on any desk to the laptop assigned to you, and here you have the ID actually of each laptop and the password. And for this first hands-on, you will use the guide number 1. We will wait for a while all of you are inside each laptop, and we will be here to answer any question that you have. Just raise the hand in the blackboard, and then we will help you if you have any question.
All right, I see that everybody is coming back to the main room, and then I can continue. So now you measured the step response, and the step response is something quite important in control engineering. I will first see if there's no echo, so if everyone can mute his microphone. So yeah, that should be solved. A step response is something quite important because that gives us a lot of insight in how the controller reacts. For instance, we have a set point of 0 rotations per minute, and suddenly we move the set point to 50 rotations per minute, as you can see here in this picture, and we apply this on this control loop. Well, what will happen is that the actual speed will try to follow that new set point and will try to go to that new set point. And the manner to which that is done depends on the proportional controller, on the proportional gain. So I said before, here we have an error here in rotations per minute. The role of that proportional gain is to translate that error in rotations per minute to a value of the current. You can see if we take a gain of 0.1, that can be a conversion of RPM towards amps, then you get this response. If you see a response like that, you can think, oh, it's too slow. You want to go to that speed quite faster, and you increase the gain to 0.3, for instance. You see that our controller is already reacting much faster, and that's normal because a smaller error in rotations per minute results in a larger value for the current, so a larger input of power, and we will go to that desired position quicker. However, we also see something very striking, and that is no matter how high we put our gain, we never actually reach the speed of 50 rotations per minute. So that's a problem. We can increase the gain, it goes quicker and quicker, but we can increase it so much by 2. So an error of 1 rotation per minute will result in 2 amps. That's already quite a lot. And you see if we do that, that you get what we call overshoot. We don't reach our speed, but a higher speed. And then we go back to the actual speed. There's also a noisy signal on the speed, and but we do not really reach the 50 rotations per minute. If we increase our KP, our gain further, we get what we call an unstable system. We amplify a small error so much that we put so much energy in the system, you have a large overshoot, and you have a large negative error, which is compensated, again an error, which is again compensated, and that leads to an unstable system. This is something that in practice we want to avoid at all costs. So we need a KP that is good enough to make it quick enough, but on the other hand, it can not be too high because then your system becomes unstable. So what we see actually is that the gain of a proportional controller leads to a system that is faster. We get a steady state value faster. So the settling time decreases, the time to reach your set point decreases, but at the same time, if we increase the gain, we get a larger overshoot, and an overshoot already hints at something that might get unstable, and that is something we want to avoid. Unfortunately, this is a so-called rule of thumb. We see that and we can understand it based on our intuition, but these rules of thumb are not valid completely. We cannot say that they are valid for 100% of the cases, far from. What you see here, for instance, is your gain KP, your proportional gain. It leads to a higher overshoot, and suddenly then a higher KP leads to lower overshoot. So there the rule of thumb contradicts. For the settling time, it's the same. It decreases with larger KP, but suddenly you have an increase and then a decrease again. So these are nice rules of thumb, but we cannot really rely on them in an absolute manner. However, the most important thing was we do not reach the final desired speed, and that's something typical for a KP, for a P controller. Why is that typical? Well, let's go back here. If, for instance, we would reach the desired speed, if we would reach 50 rotations per minute, then the error would become 0. A 0 error amplified with whichever KP would lead to 0 current. So you don't drive the setup anymore. You don't drive the machine anymore. And that means that suddenly there will be no more speed. So with a KP, we get a so-called steady state situation in which KP is just, in which the error is just enough to maintain the motion. There is just enough error to maintain the motion and to have a current. Of course, we want to avoid such situations, and that's why we add an integral control to our proportional control. An integrator integrates, you may remember that from math classes, but we want to avoid difficult math here as much as possible. Actually, what an integrator is doing is summing up. So you see here the error in red. The integrator sums up all the values he sees. So here you see in green the integral term. The integral term starts at 0 because there is no error given at the input. The more errors we give at the input, the more you see that the integral term increases. So he actually takes the surface below this red curve. And the further in time we go, the more the value of the integrator increases. Now, why is that very interesting? It's very interesting because when the error gets 0, when we actually have a 0 error, the integral term keeps its value. In this case, it keeps the value of 150 milliamps, and that's enough to keep the system rotating at 50 rotations per minute. So the integrator is there to help you achieve the desired value. So it is necessary. It is really necessary. It is not always necessary. We will see a situation today in which you don't need an integrator. And if you don't need an integrator, it's also nicer to avoid an integrator, because we will see an integrator has some disadvantages of its own. But here it can be necessary to have an integrator to have a 0 error to actually achieve your desired speed. On the other hand, you also see here the proportional term. The proportional term takes the immediate input, the immediate error, amplifies it, and that's it. So once the error comes 0, we reach our actual speed, then the proportional term is not playing a role anymore. It's all depends on the integral term. Here you see we had Kp of 0.5. We took Ti, the so-called integral time. Ti is a measure for the strength of your integrator. Well, if Ti is 500 milliseconds, this is our response. What we see here is we reach the desired speed, yes, but we need 400 or 300 seconds to reach that speed. It's quite a long time. We want to limit that. And what is the error here? Well, the error is actually, you see a so-called immediate response here. And if you see something immediately happening, that will be due to the proportional term in your controller. Then after that immediate effect, you have a slowly building effect. And a slowly building effect is very typical for an integral controller. The integral needs time to sum up all the terms you add to them to reach the certain value of that amount of current to drive the machine. So actually what we need here is a quicker integrator. We need an integrator that is quicker. So what do? We decrease the TI, the integration time, to 100 or to 30 or to 10 milliseconds. As you can see here in the general formula and the general building blocks of your controller, the integral gain is 1 over Ti. So that means that a lower Ti value actually gives you a stronger integrator. The lower the Ti value, the quicker your integrator, but also the stronger your integrator. This is an integrator that is too weak, too slow. You reduce Ti and you get quicker integrators, but also stronger integrators. And you see if your integrator gets too strong, you almost have this effect, which the blue effect leads almost to instability. Large overshoot, also the settling time really increases. Well, that's an effect of a too strong integrator. The integrator has the tendency to make your system unstable. In this case, we used an integration time of 0.5 milliseconds, really short integration time. 1 over Ti is quite large, so you get an unstable system. That's the reason why if you don't need an integrator, don't use the integrator. But in many cases, you will need it, almost standard. It's almost default that you will need it, but I will show you how to know when you need it and when you don't need it. Well, if you need it, then be careful with the integrator. Be really careful. Start with a large value of TI, decrease the value of TI little by little. If you have the green response, the value of TI is too large, then decrease it little by little to have a good response. But once again, these are rules of thumb. We say that by decreasing TI, the settling time increases, the overshoot increases, but again, it's not valid for all cases. These curves, for instance, I showed them, but these curves are also not valid for all cases. These are very specific for one case. When we would have these curves, it would be very easy. We just choose here this time TI, then we have a minimal settling time, also a low overshoot, but we cannot because we don't know these curves. For applications, it's also difficult to measure them, trial and error, and if KP shifts, if we have a different KP, then that curve can look completely different. So the rules of thumb are very interesting to know. Do not forget them, but we must know that you cannot do everything based on those rules of thumb. Okay, maybe it's also time for a little interaction, and I would like to ask you, how do you design your controller nowadays? Do you do that with trial and error? Do you do that with a specific method? Maybe you use auto-tuning. I'm very curious to know. I will also ask for my colleagues from the University of Ghent and from the University of Antwerp to not participate in this poll, because we want to know what the opinion of industrial partners are. That is quite interesting for us to know what they think. So you can click 1, 2, 3, or 4, and then we know if you use trial and error methods nowadays, if you use auto-tuning, maybe you have a good method of your own to design KP and TI, or maybe you feel the need for a better method without the E. I don't see the reactions coming in.
It doesn't seem to respond when I click on it.
Okay. Maybe I will relaunch. Yeah, now I see. Okay, I see that the people are responding actually. Yeah, now we get your opinion, which is very valuable for us. So I will show the results in a minute. So yeah, that's it. So these are the reactions. So I can see that half of you is happy with auto-tuning and the other half needs a better method. Okay, maybe we can also convince the people that are now using auto-tuners that we can provide them with a better method, because auto-tuner is very good if you have it, and it doesn't always work in any case. But let's see where we can come with those techniques. All right, one thing for integral controllers: if you have an integral controller, if you need an integral controller, use the anti-windup, because windup means that the integral value can get too large. For instance, your integrator indicates that he wants to put a current of 2 amperes in your machine, while this is a machine that can only handle 250 milliamps. It's a small motor, and your integrator wants to put a much higher value in. Your integrator is not aware of the fact that your process is saturated, and if your integrator is not aware, then the value can get really large, and that leads to very large overshoot and sometimes to instability. If you have any software where you have an option to have the anti-windup cancelled out or the anti-windup active, always put on the anti-windup. Always. There's no reason why you wouldn't select the anti-windup option unless you want to educate students and you want to show the effect of an integrator which is not limited, but always limited. If you design a controller, if you program a controller yourself, it's very simple. You just use an if then else structure. You keep track of the integral value. You say once the integral value exceeds the actual saturation for your process, then you limit it again to that actual limit of the process. So your integral value should be aware of the saturation. In most cases, you can click on or click off the in anti-windup. Always use that option. Finally, you heard PID controller. We have also the derivative control action, and what the derivative control action is doing is dampening the response. It's very interesting if you can use a D action, if you can use derivative control. It also goes by a time TD. If you increase that time TD, you damp the response more. So what you see here is the blue curve is damped a little bit to the yellow one with TD 0.1 seconds. It's damped a little bit more to 0 by TD 0.2 seconds, etc. Very interesting, very nice if you can use a D action, a derivative action. You see here, these are not measurement results, those are simulation results. Why is that? Because on our setups, we cannot use a derivative control action. Why can't we do that? Because derivative controllers react very badly to high frequencies. And everyone familiar with electrical motors know that their drives use pulse width modulation. Pulse width modulation means that you put in lots of frequencies. So by default, there are high frequencies in your speed signal. Those high noise signals would be amplified so much by your derivative action that it would get unhandleable. So a PID controller is very uncommon in electrical drives. You will not see it. We will not apply it. A PID is applied in temperature control, in flow control, in maybe the control of a certain volume, but we will not see it in electrical drive applications. We will only see the PI controller. Once again, of course, there are rules of thumb, but they are not generally valid. If you dump too much, if you have a too high TD, then your system becomes too slow. But again, it's very difficult to know where this point is situated. All right, so we saw that lots of you use AutoTuner, but other people said we want to know a good method to design a controller. I also showed that you can get an unstable system, so that's also not really preferable. So how do we start? For God's sake, how can we start with the first good guess for the settings of your P, I, and D controller? Well, actually, a first approach I want to show you is a really nice approach because it's almost on any case applicable. You can almost apply it on any case, even on cases that are already running, even on cases that are already operational in the field. You can do this kind of measurement and have new settings for your P, I, and D controller. This is the relay feedback method. And what is the relay feedback method doing? If it sees a positive error, it puts the input of the system at maximum on. If it sees a negative input, it puts the input of the system at the most negative value off. So it's a relay controller. We replace the PID controller that might be there already by just an on-off controller, which switches between maximum positive and maximum negative, depending on the error. Positive error means sending positive signals to the system. Negative error means sending totally negative maximum values to the system. Based on that, your system will start to vibrate around a certain value, and that vibration with one certain frequency is very interesting. From that vibration, we can measure the amplitude, we can measure the period, and by measuring the period and the amplitude, we can use these values here or this table to have good guesses, good first guesses for your proportional controller, your integral controller, and your derivative controller. You can wonder, how can we apply this in practice? Nobody will allow you to go to an installation that is already running and let you switch between maximum positive and maximum negative. Imagine you have a conveyor belt and you have to drive this with maximum positive current and maximum negative current, and the conveyor belt would go at very high speed to right, then suddenly at very high speed to the left, to the right, to the left. You will get large vibrations. Nobody will allow you to do that at a process already running. That's true, but we can play actually with the value here of this controller. We do not necessarily need a relay to switch between 0% and 100%. This is a flow controller. We want a flow of 80 liters per minute. That's a process already taking place. We want to maintain that flow of 80 liters per minute. Maybe this is a process already taking place. In that case, you know, you can measure, okay, we had a PID controller, but we want to improve the PID controller value. But by that PID controller, we saw that to have a flow of 80 liters per minute, we need a value, we need an excitation and actuation value of 40%. So by sending 40% as an actuation value to your process, we get 80 liters per minute. That's the response. By sending 40% as an excitation value, you get 80 liters per minute as an output flow in your system. Then, of course, if you go to a factory where it is important that the process keeps running, you will not switch between 0% and 100%, because then the flow might vary between 0 liters per minute and 200 liters per minute. You limit the saturation. We limit the relay between 39% and 41%. And then you get a small vibration on the actual flow, and maybe that will not be harmful for the rest of the factory. It's not a problem that you have a small variation around that 80 liters per minute. Or maybe that variation is too low to measure it. You put your relay at an on value of 45% and an off value of 35%. You can maintain your set point. We maintain our set point of 80 liters per minute, but now we have a variation between 70 liters per minute and 90 liters per minute, and that allows us to do a measurement, but it also still allows the rest of the factory to work with that system. It allows the rest of the factory to have a flow which is around 80 liters per minute. What is possible is that you have a system, a PID controller already pre-programmed, and you cannot replace that PID controller by a relay. For instance, this is the case at our setups. We cannot simply say, okay, take out the PID controller and take a relay switching between 35 and 45%. It's not possible with our drives. Or we have to program things ourselves. So that hinders the implementation. No problem about that. We can just do the same with a classical PID saturation. We eliminate the I, we eliminate the D, so we put the I action inactive, we put the derivative action inactive, and we take a gain Kp, which is very high, which is very, very high, and we use the saturation to define the switching values of our relay. We switch between 35 and 45% by setting up the saturation in a good manner. We disable the I, we disable the D, and we're only relying on the proportional gain Kp. And in that way, you can also do that measurement. I will give the floor to Santiago, which will show you very briefly how we do it in our drives. This is a demo. You do not need to do anything hands-on, but we want to demonstrate that this is also possible. The relay feedback is also possible to execute at our setups.
Okay, so for this demo, the first thing we will do is change the gains of the controller. So we go to open loop, close loop. We click on the speed controller, and then we will have the PI structure. So as Sten said, we make the integral time 0, and we will give a high value here to be able to produce or to make the effect of changing or the on-off into the controller. Now we will need to limit the torque. So we go here, torque limitation, and we have the upper and lower limit. For that, I will use the Excel file that was provided to you. So here we have the relay feedback tab, and here we will write the value of our torque at the velocity we wanted to achieve. When I did the first demo, I moved to 500 RPM and I got 0.34 Newton meter. Here we will have the max and the minimum value of the on-off signal. So it's adding 83% and subtracting 83% for this main value. So we will add that value for the upper limit, 0.624. Then we close and we see that the value is updated here. We do the same for the lower limit, which is 0.057. And that will ensure that our signal on-off signal will be in between the range that we want. Now, we can go to the control panel and assume control priority. Don't forget to untick the active box. We accept. We have here a shadow in the alarms. Always that you get this shadow here, blue shadow, go there and acknowledge all to avoid any error.
Okay,
Then,
I will take over from Santiago because now he will do a measurement, but since we're short on time, I will skip immediately to the result of that measurement, if that's okay with you, Santiago.
Yes, okay.
So what we have then is this result. So actually we see that the value Santiago put in the saturation, you get here, that's the driving value. Here is the actual speed at that time. So with that combination, we have enough data to apply our method here in this table. We know the amplitude of the output signal, we know the period of the output signal, and we know the actual input of the system. With those values, you can design your PI controller, and you see this is the response. What we see there is it's not that good. You get serious amount of overshoot, lots of vibrations. So it's not a perfect controller, far from, but it is a good controller which is stable. It's not unstable behavior. You have a very good first guess of KP and TI, because KP for one application can be 10,000, for another application it can be 0.1. For one application, TI can be 2 seconds, for another it can be 0.5 milliseconds. And if you don't have a first guess, you might make your system unstable. With the relay feedback, you know for sure that you have a controller designed which is at least stable. And then based on the rules of thumb and based on your feeling, you can start to play with the values a little bit. So that's the idea behind relay feedback. Apply it. You won't have a perfect controller, but you will have a very good first guess. And relay feedback is applicable on all kinds of systems. What is important is looking at the unities. Here, Siemens starter, for instance, defines the speed in rotations per minute. However, the KP value is defined in Newton meters second per radians. So actually what is happening is that the error that comes in is automatically translated to radians per second by Siemens, but you don't see it. And we have to put our KP value in Newton meters per radians per second. Why do I say that? I say that because all our measurements will be in rotations per minute. That means that by applying our methods, we will come to a value KP, which has a unit Newton meters per rotations per minute. And of course, that unit, Newton meter per rotations per minute, should be conversed to Newton meters per radians per second by multiplying it with 60 over 2 pi. You multiply the unit you multiply the KP value we become with our methods by 60 over 2 pi, and then we have it in the right unit, Newton meters per radians per second. Units and control engineering, it's something you have to take into account. You have to be aware of that. What is the unit of my KP value? And here we saw it's Newton meters per radian. We did the measurements in rotations per minute, so we have to translate that. We have to convert that. It's very often control engineering issues are due to this unit. So it's something that you have to consider carefully if you're designing your controller. Here is the relay feedback result we obtained. You see here, if we apply this step, this is the step response. We can do a few things now. We can play a little bit with our KP value. So here you see we made KP value a little bit higher, and then we get a red response, or a little bit lower, we get the yellow response. So we can play a little bit, but sometimes we have counterintuitive results. For instance, here we increased our KP value, but by increasing our KP value, we get a more damped system. So I said the rules of thumb are not always generally applicable. It's something you can play with a little bit based on the feeling and based on trial and error. Another thing is that you see we have a large overshoot here. We have quite some overshoot. Actually, that's normal. Or at least if you consider the system, it might seem normal. You have a system that is at standstill, and in 0 seconds, you suddenly want that system rotates at 500 rotations per minute. So you switch from a desired speed of 0 rotations per minute to a desired speed of 500 rotations per minute just in the blink of an eye. And of course, that's impossible. Your system cannot accelerate from 0 to 500 seconds to 500 rotations per minute in 0 seconds. It needs some time. So here your controller does its very best to reach this speed as fast as possible, and this leads to overshoot. A solution for that is applying a pre-filter and saying, okay, we know that the system cannot respond immediately. We know that the system needs some time. And therefore, we filter very sharp input desired values with a pre-filter, and this is a first order system. A first order system needs 4 times the time constant tau to come at its final value. So this time constant you can define like that. What we've done here, we saw the time that was necessary to go from this point to the first peak was 12 milliseconds. We measured it in practice, 12 milliseconds, and then we can design a pre-filter with a time constant of 12 milliseconds. You see here, then you get the light blue response, which also has some oscillation, but we don't have the actual overshoot anymore. We will never move faster than 500 rotations per minute, which can be a problem in some cases. Or we maybe increase that time constant of the pre-filter. Here we decreased it, to 3 milliseconds. Then you see it almost has no influence. We see almost no difference between the dark blue and the light blue. And then if we go to 24 milliseconds, we have a big difference between the dark blue and the light blue. And then we get a really filtered signal. So we can use the pre-filter for that purpose.